Welcome to Chapter 2, Chemistry. So here we'll look at the language of chemistry, the fundamental concepts, matter, how it's organized, the subatomic particles, why and how they form chemical bonds, and then we'll look at the different molecules made by building up bonds. Okay, basic principles of chemistry. So chemistry is the science of matter, what it's made of, and how they interact together. Matter, it's anything that has mass and takes up space. So mass is the amount of matter a substance contains. On Earth, we can kind of use those words interchangeably, but if you're on a different planet with a different amount of gravity, then your weight's going to be different, whereas your mass would be the same. So if you weighed 150 pounds on Earth, you would be less weighted on the moon. Whereas if you went to somewhere with higher levels of gravity, your weight would be heavier, but your mass would be the same in all three cases. There are three general forms of matter. If you get really complicated, there are more, but for our purposes, as far as we need to know, solid, liquid, and gas. So you could tell by looking at something whether it's a solid, liquid, or gas, but what makes it that way? Why? Solids have definite shapes and definite volume. That doesn't change. Liquid has a definite volume, but it has an indefinite shape. So if you pour a glass of water from one glass to a different shaped glass, you still have the same volume, but it changes shape to fit its container. And then last, gas. Gas has an indefinite shape and an indefinite volume. So their gas particles are moving around, and you can change the amount of space they take up. So if you've got a plastic bottle with air in it and you close it, close the container lid, if you squeeze it, you've got the same amount of gas in there, but you have less volume. There, the pressure would increase, but overall, indefinite shape and indefinite volume. All matter is made up of elements. So elements we have on the periodic table, and they have chemical symbols. So here's the most important ones for our body: oxygen, carbon, hydrogen, and nitrogen. You can see the book has really nice tables of the different elements in the body. All elements are made of atoms. An atom is the smallest piece of that element that still has all the properties and characteristics of the element. There are physical characteristics and chemical characteristics of each element. So gold, for example, a brick of gold, if you think about it, you can see it. It looks gold, it's hard, it's dense. Those are its physical characteristics. Whereas chemical characteristics would be about how it reacts with other molecules, what bonds it makes, what compounds it makes. Okay, let's look at the parts of an atom. Atoms have a couple different parts. They've got in the middle a dense cluster of very heavy, relatively heavy, parts, and then a light cloud of the lighter subatomic particles. In the nucleus, you've got the protons and the neutrons. Those are the heavy parts. The protons, P+, have a plus sign because they have a positive charge. The neutrons, N with the 0, have no charge. They're neutral. And electrons, E-, have a negative charge. So an unreacted atom of any element have the same number of protons as electrons. So their overall charge is 0. Once they react with other molecules and they give away electrons or gain electrons, then their charge can change. Okay, let's look at different isotopes. So an atom of carbon, for example, always has 6 protons and 6 electrons. That doesn't change if it's unreacted. But what can be different between different atoms of carbon is the number of neutrons. You can have 6, for example, like this, and then the weight would be 12 total. Or you could have 7, and then the total weight would be 13. That would be its mass number. The atomic mass number is an average of the relative numbers of each type. So there's a lot more carbon molecules that are carbon-12 than are carbon-13, because the atomic mass number is very close to 12. Sometimes isotopes can be radioactive. So if an atom's radioactive, what that means is when it loses a neutron, it's radioactive. It releases energy. And we can use that, it's a predictable rate over time. We can use it to age things. So they'll do carbon dating. Let's look at a couple different types of things that are made when we have different atoms bonding together. First, you can have an ion. Another word for an ion is an electrolyte. And that's an atom that's either gained or lost electrons. So there it has a charge. Like sodium would be Na+, potassium K+, chlorine Cl-. A molecule is two or more atoms sharing electrons that are bonded together. So for example, oxygen gas, O2, is a molecule. Sugar, like glucose, C6H12O6, is also a molecule. A compound is very similar to a molecule. The only difference is that it has to have at least two different types of atoms. So now oxygen gas, O2, is a molecule, but it's not a compound because it's only got oxygen atoms. Whereas the sugar, the C6H12O6, would be both a molecule and a compound. Chemical bonds. This is so important. Everything that happens in our body within our metabolism is based on chemical bonding and how things react together. How an atom wants to react with others is based on its electrons. It's based on the number of electrons in their outermost shell. Another term for the outermost shell is the valence shell. Atoms always want their valence shell to be full. So the first shell is full with 2 electrons. The second shell fits 8. And so does the shell after that. So here carbon, for example, has 4 electrons in its valence shell. This is important for why organic molecules work, why we use them in our body. Carbon wants to share 4 pairs of electrons so that it can have 8 total. First type of bond we're going to look at is ionic bonds. That's where one atom wants to get rid of an electron and it gives it to another atom that wants it. Let's look at an example. So here we've got sodium and potassium. So here's sodium. In its valence shell, it has 1. So the easiest thing it can do is get rid of this atom, and then that lower shell is full. So that goes down, and it gives it to chlorine. Because look, chlorine has 7 of 8. It's missing an electron here. So we take that electron, and we give it to chlorine. So sodium has lost an electron. It's lost a negative charge, so now it's got 1 more proton than electrons, and it's positive. Chlorine adds an electron, it adds negative charge, so it's got a negative charge. And now the positive charge of sodium is attracted to the negative charge of chlorine, and you've got this attraction is a bond forming between the two. NaCl, that's like table salt. Next we have covalent bonds. Covalent bonds are where 2 atoms share at least 1 pair of electrons. So they're both atoms want electrons. So hydrogen has 1 electron on its valence shell. It needs 1 more. Oxygen has 6. So it's going to share a pair of electrons here to get 7, and a pair here to get its 8. So you can see through the chemical reaction now we've got pairs of electrons. And what those electrons are going to do is they're going to circle from the hydrogen to the oxygen and around. So sometimes the oxygen's valence shell is going to be full, and sometimes the hydrogen. For the atoms, it's better that their valence shell is full some of the time than never. So they're more stable this way. And we just made water. What's really interesting about water is that they don't share equally. Oxygen is electronegative. It's called an electron sucker. So those electrons are more likely to be around the oxygen than the hydrogen. Because of that, the oxygen has a slight negative charge, while the hydrogen has a slight positive charge. That means the molecule is polar. It's got charge. That fact is why everything can dissolve in water that does. Atoms can form single bonds, where you just share one pair, double bonds, where they're sharing two pairs, or triple bonds. Nitrogen makes 3 bonds, so it shares 3 pairs of electrons going back and forth between the two. And then here we're looking at how carbon does it. So this is what's the backbone of organic molecules. And there's water. And you can see the slight negative of oxygen and the slight positive of the hydrogens. The last type of bond we're going to look at is weaker than the other two. The other two, ionic and covalent, are very strong. Hydrogen bonds are much weaker, and they form between molecules. So they're atoms of one molecule or attracted to the atoms of another. So you're not making a new chemical bond completely, it's just a slight attraction. And how you get that is when the hydrogen is slightly positive and it's attracted to something that's slightly negative. So in water you have all these hydrogen bonds between the positive end of the hydrogen and the negative end of the oxygen of another water molecule. So that's weak in individual bonds, but when you have a lot together, it's very strong. So if somebody jumps into the water and they belly flop, that surface tension that hurts them, that's the hydrogen bonds. That's what they're close. Now let's look at chemical reactions. So anytime you build a bond, like an ionic bond or a covalent bond, or break one, that's a chemical reaction. So what you have when you're going into the equation is the reactants. Those are what you start with. Then they go through the reaction, and at the end you've got the products. So here you've got hydrogen gas and oxygen, and those come together to make water. All these reactions, remember, are your metabolism. So how do we do this? How do we make bonds or break them? Energy is the capacity to do work. So there are different types of energy. There's potential energy and kinetic energy. Potential energy is stored energy. Kinetic energy is energy in motion, energy in use. So potential energy examples would be like chemical energy. We store energy in chemical bonds. We'll look at ATP, this molecule, high energy bonds. When we want to do work in our cells, we'll break it, release the energy, and do the reaction. And then the law of conservation of energy is neither created nor destroyed. Within a closed system, you're going to have the same amount of energy at the beginning as at the end. But like our Earth, our body is not a closed system. So whenever we do a reaction, some of the energy is going to be lost to us as heat. And then it leaves. So anytime you're doing a reaction, you need to put in energy before you get the product. And a lot of the times, that energy that you need to put in, called the activation energy, is higher than we would naturally get in our body. So if you are waiting for a reaction to occur on its own, it's only going to occur at really slow rates. But what our body does is it uses catalysts to help reactions go much faster. So what they do is they decrease the activation energy. They make it easier. They bring things together. They increase the rate of reactions up to millions of times faster. Our bodies use biological catalysts. Those are called enzymes, and we'll look at them more later.